Quick show of hands. Who was here last year? That's good. More. Who will come back next year? No, let's ask that later when we have more people. Who saw Lisa's talk last year? Do you remember how she made a beach party by making a shark spitting out the people, essentially reversing the Jaws movie? That was about games, and this time it's going to be about art. I'm really looking forward to that. So here we have from Berlin, Ember, JavaScript, Rust, Clojure developer Lisa Parsing. Thank you.
Hello, ClojureD. Thank you for the intro. The Jaws joke is still one of my favorite ones. Today we will not talk about games specifically, but like abstract some of like games need to be fun and they need to be about stuff. Like strip all of this away, and then you have like interactive art. And we will take a look at like what this might be looking like. But before that, a little who am I for like people who have not seen me last year and is like, what is all of this about? So hi, I'm Lisa. I am based in Berlin. I do mostly web dev in various languages, and I do like small little weird video games in various languages. I help organize the local Clojure Bridge chapter, which is free Clojure programming workshops for women and non-binary people. And I also help out at crypto parties, which are informal gatherings where we teach people privacy enhancing and privacy preserving open source tools for their digital selves. But most importantly, I like creating weird stuff with code. A lot of the talks today are like about, serious things that you need at work, but this is not about these things. This is about like, what can we do with like code that might be, just for ourselves, things that make us happy. And for a long time, like I've been doing games, but I also like recently discovered that I would actually like to be an artist. Who had the same thoughts, like, oh, I would do some art, like show of hands, it's like, cool. Who have you actually tried, but like who failed maybe even at the first step of, I don't even know where to start? This talk is for you. And I think like the combination of code and art is something that is that goes hand in hand for a long time. So I'm not sure if you're familiar with the hacker's ethic. It's like something that like appeared out of a book. It's called Hackers, Heroes of the Computer Revolution, and it deals with like the early like researchers in the 60s and 70s and like the cool stuff that they were hacking. This is a list of the hacker ethic. I know that a lot of people today still are like, this is actually the ethic that all hackers should live by. And like there are some like controversial things. This is why I also put a link to a transcript of a talk by Alison Parrish in here, where she talks about like what are the specifics of why the ethic as it is written down is problematic. I highly recommend reading this. But there's one thing where I can say is like, oh, there's one point there's like definitely not, like maybe 2 points that are like not problematic at all, but we're gonna look at one of them. And this is, you can create art and beauty on a computer. And this is like, yes. So then it's like, okay, if you like, once you start with the topics, like maybe you should like read up on like what does it mean? What would people expect when you like start working on this stuff? So I looked up art on Wikipedia, as one does. And the definition on Wikipedia is actually quite nice because it says art is like is like creating an artifact that is like sort of like that stems from like a people's brain, basically, like paraphrasing. It's like an artifact, like a program. Like we can do this, okay. It's like there's definitely coding in there. The other part is that it says, it is intended to be appreciated for the beauty, or like among other things. So it's like, okay, beauty. That's weird. What is beauty? Wikipedia says beauty is a characteristic that provides a perceptual experience of pleasure and satisfaction. And if you make games, it's like experience is something that you can create easily by like letting people play with something. So it's like, okay, this is definitely something that is within the scope of my capabilities. So let's do it. Let's make art with computers. And then started, of course, like in this day and age, you're never the first person to think of something, sadly. So there's like, if you Google something, there's like people who have done it before, which is okay. So we can like draw inspiration from this. So research time. There is, for example, the Recode project, where people re-implement art that has actually been like written by people in the 50s and 60s with like very low computational power, and they've already made art. So this is like very old stuff, and then people these days just like, oh, let's do it in JavaScript, and then like have this like archive of things that have already been done, so that you can look at it and see like what's possible. And like, this is really cool. And this is like, it's basically a computer art museum, computer art archive, which is kind of nice. And then there's also like a very active community that like of people that like post their art on Twitter, for example. So this is an image that clojureD, or like however you pronounce that, created, and this is like totally generated from like code, and it's just like, if you look at it, it's circles that have borders and that like have little shadows, and like the shadows like this nice noisy texture. I was like, oh, this is really cool. And he does very amazing things. So if you're on Twitter and you like nice pictures in your stream, highly recommend. There's other people who generate like patterns like this, and then they're not just like generating them, but they have like pen plotters drawing them for them. So this like, in the end, you have a piece of paper that is like a robotic hand, if you will, like the pen plotter on a 2D axis draws the stuff that was generated. It's like, okay, wow, cool. You can like take it a step further into like into the world of like tangible things. On Nervous, you can buy lamps that are 3D prints of organic like generated like structures. And it's like, you can like spend hundreds of dollars on like a generated lamp. And it's like, okay, that's cool. You can do stuff in Unity, and this is an example of like someone who created you can live distort things in Unity with like a MIDI controller when you like turn on knobs. That's actually a video. It's just a screenshot of this. And it's like, okay, that's fancy. Like other input devices, and like Cashflow is another like generative artist, and he's like, okay, we can actually use like input to have people figure out like magic numbers and physics, and you like turn the knobs and it's like fancy patterns. I was like, okay, whoa, okay, this is pretty cool stuff, but it's like, this is not something we can do on our first try. So expectation management time. Let's set us a small scope and try to stick to that. Let's create something that looks artsy, that is somehow generative. So like, it's not always the same when you run the program. It's like different every time. So there's like something that's like creating stuff for us. Something that allows interaction, because interacting with something has people like their brains create an experience. Like, is this fun for me? Like, do I have like some sort of this like satisfaction factor that is crucial to like the beauty of the artifact that we want to create? And of course, we want to do it in Clojure or ClojureScript, because obviously. Okay, let's pick a tool. And once you start like looking at what kinds of tools people use to like produce art, there's definitely the number one choice for if you're starting out is processing. And processing is a language that was designed for actually non-coders to like ease them into like expressing their artsy feelings in code. And it's originally implemented in Java. So if you want to do Clojure, there's a wrapper around this. It's called Quill. It's really cool. We teach it at ClojureBridge. There's also P5.js, which is the part of the processing thought and thinking to JavaScript in the browser. And there's also like a ClojureScript equivalent, QuillCLJS, which under the hood actually uses processing.js, which is a more of like informal clone of this thing, or like re-implementation that existed before P5.js, but whatever. And I think I will stick to QuillCLJS because the abstraction is really nice, the wrapper is really nice. I tried using P5.js with just accessing through like the global namespace, but that was like kind of messy, and the translation from like the very yeah, imperative to like object-oriented like examples that exist out there into the functional thing is already hard enough. You don't need to like fight like the abstraction to ClojureScript yourself. So ClojureJS. Okay, let's start exploring. And because I really like the circles example from Manoloide, let's start exploring with circles because they're really nice geometrical shapes. They were probably my favorite geometrical shape. You can, of course, do this with your own favorite geometrical shape. Let's start with random. And if I now had the chance to like rename this talk, I would like just call it just use random. It's cool. So with circles, we can have random positions, something like this. Let x random like somewhere between 0 and the width, and let y somewhere between like 0 and like the height of our thing. Q is, by the way, like the namespace for quill in my examples. We can have random colors for our circles. So let's have like RGB, like something random, like from 0 to 255. And then it's just like, yeah, will be cool. Random sizes. So we have a radius, and we're just going to use like something between like 10 and 50. It will be so cool. And then we just like put this in the draw state, so like the function that is like executed 60 times per second. In the example that follows, I actually reduced the interval, so we only have like 5 frames per second. So that's just like that it's not like flimmering all the way, but basically we just use a fill color that we generated randomly from RGB, and then we draw an ellipse, which like given the same radius for horizontal and vertical, we get like a nice circle. Okay, let's run this. It's beautiful, but it's so random. It's kind of like where's my intention? Where's the technical skill that led me to the creation of this artifact? It's like I think we need to talk about distribution of values. Or to be more specific about the distribution of random values. Talk about uniform distribution, which is what we saw right now. Each value in our range has the same probability of getting chosen. So this is literally what random is. It's like you give it a range, and then it picks a random value from that range. And if you plot like or try to plot the occurrences of like the values on the range, they're like more or less like the same outcome for everything. So it's like, okay, so it could literally be anywhere, and it like have any sort of like color on this thing, and it's like, this is cool and all, but it's not focused. Luckily, there's like other forms of distribution. We could have a normal distribution of values. This is also called Gaussian or Laplacian distribution. And in this distribution, we have the values like sort of cluster around an average, which is called the mean. And so the values that are closer to the mean have a higher probability of getting chosen. We have a second factor, and this is the standard deviation that says how closely the values that cluster around the mean are like distributed. This might sound weird, but here's a nice graph. So in the left example, we have a small standard deviation, so it's like they're like closer together. And on the right side, we have a higher standard deviation, so they like flatten out a bit. Cool. So in ClojureJS, we have random Gaussian, which implements just this. It's normalized, so we get a value between 0 and 1, so like a floating point value, which is what it says. And then we can like use it for like our purposes of like having like we want this like somewhere between somewhere on our canvas, but like we have 0 to like maximum width. We can write a little function that takes a mean and the deviation, and then we multiply the deviation with the value we get from random Gaussian and like add the mean to it. And then we can just like replace all our randoms with normal distributions. I also, in this example, exchanged the RGB color mode to HSB, and if by the end we have a little bit more time, I can go into this. This is my little bonus, but it's just like a different way of this like displaying colors. But yeah, let's see how like our normal distribution thing looks like. Run the sketch. Okay, let's more focus. We like have some sort of like clustering in the center, which makes sense because we said we want to like the mean is like the middle of the width and the middle of the height, and we also like with HSB I chose a value like a hue value that we like kind of like sort of circle around, but I'm still like, I like the positioning, but the color's off. Like there's always this like little blue. I could probably like tweak it a little, but I want something else that like normal distribution may not be able to give me. There's also custom distributions. Yay! It's basically bring your own probability function. So this is cool. And one of the many examples that you could use for this is called Monte Carlo. It's a little algorithm that roughly works like this. So we have a Monte Carlo function, and then we start a loop. And then we pick a random value from 0 to 1. And then we assign we get a probability from this random value. In this case, I would just use the random value itself as probability, but you could also, I don't know, multiply the random value by itself or whatever like fits your purpose or like whatever you want to do. And then we pick a second random value. And then we say if the second random value is smaller than the probability, return us our random one, like the random thing that we have. If not, let's start the loop again, pick new random numbers. So we have this like sort of, we like kind of like generate random numbers ourselves. In this case, with like assigning the probability just from like the random number that we first chose, we get this like the higher the number, the greater the probability is that it gets chosen. But you can do something else with it. In fact, you can always do what you want with it, which is nice. So we could either just use, instead of random Gaussian, just like put our Monte Carlo function into like our custom distribution, or like make a custom distribution method that does basically the same, but instead of random Gaussian, we use Monte Carlo. Or we can just like map the Monte Carlo value to like another value. A little explanation to the map range function here. In the original processing, it's just called map, but we know that in functional programming, there's a different map. So they thought like, oh, we should probably rename this into map range. And what it does is it takes a value, in this case, whatever Monte Carlo gives us, and then it's followed by the values that define the range that this value could be like. So we know that Monte Carlo will either return a value between 0 and 1. And then we want to say, like, okay, this value on this range should actually represent like a value on a different range. So in this case, I'm choosing brightness. And brightness, like RGB, can have a value between 0 and 255. So let's say, let's map this Monte Carlo value between 0 and 1 and map it to a value between 0 and 255. And this is what map range does. And I'm using this on brightness. OK, so let's look at the colors. A bit better. So instead of like just like assigning like different colors of the same color degree on the color wheel, basically, we have different like brightnesses, but they're still like all in the same range. It's like the blue that we had before. It's not as off-putting, and like I quite like it. It seems like okay, we have a color spectrum. We can work with this. The other thing that I don't really like is the way that the dots jump, the circles jump like on everything. So it's like this kind of. As I said, I cheated a bit. I said I lowered the frame rate so that if we were running this with 60 frames per second, it would just be like blink, 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 and you wouldn't know what's going on. So this is why I set it down to 5. But oh wait, there's a different thing. We can also play with it before we get into before we address the blinking issue. So I actually want to click on this link because let me show you. I have this. The uncolored circle should indicate my mouse position. And turns out cool CLJS is not playing well with the JS library for my slides, which is where this weird offset is coming from. It's like So this is why I made little standalone things. We're gonna do the same. And then we see it's like, oh yeah, this is actually now my mouse position. Okay, so we have a little dot, and then we can like maybe just like assign random dots and like play with this. And this is the first time I introduce state in the sketch. So I'm like, whenever I click, I like pick this, pick the mouse position of where I clicked, but then I just like have it like random, like give it a little like range of like where I can, where the circle should appear. So it like kind of like randomly like jumps and appears around the original mouse position that I picked. So like this is like nice, it's like bubbly, and I can like, it's sort of like drawing, but like not quite. And it's like, okay. It's fun, but we can improve. And I already like accidentally teased this, but there's a certain like, yeah, smoothness. You know, it's like it needs to be cooler in the way the dots jump. It's like too hibbly. Like no. And when we talk about smoothness, we need to talk about Perlin noise. So this is really cool. Perlin noise. Perlin noise is an algorithm that produces a range of like pseudo-random values. Why pseudo-random? We go through this in a second. Why is it called Perlin noise? It was because it was developed by Ken Perlin, and he thought of this when he needed to generate textures for the original Tron movie in the 80s, and he needed something that looked sort of organic, but he didn't want to like have to like, you know, draw it all by himself. So he's like, okay, I need a program to solve this problem for me. Okay, so what does noise do? Noise is like basically every other thing returns a value between 0 and 1. If we like look at this on a graph, you see on the left side with one-dimensional noise, and you see that this is like a sort of like continuous movement of like, it's still like sort of random. It's like, will the next value be up or down? But it's like, it's continuous, and it like makes sense, looks sort of like organic. Whereas on the right side, you see random is just like random, where we have this like uniform distribution of values again. So Perlin noise is all about being organically looking and like nice. The thing about the noise algorithm is that as opposed to random or random Gaussian, you can just call the function and it will give you a value. Noise on its own or with like just one argument will give you one, like it's basically a coordinate on an already predefined line. And this, so in the, let me go back. In the noise one, in the one-dimensional noise, we see this as one line. And if I pick one value, it's sort of like the interpolation between like the previous and the next value. So it's like, we know we have two neighbors, and this is like the continuous line that we have. And once you start your program with noise, this axis, this line for one dimension is set. And for each coordinate you give it on this line, it will return the same value. So always calling noise with, for example, 3 will always give you the same value. So we kind of like need to think about it. It's like, okay, this is a bit weird. And one more that, I'm coming back to that. But if you call, you can also have a two-dimensional noise. And if this is not just like a line then with like a previous and the next neighbor, but two-dimensional noise, for example, is more like a grid where you can have like up to 8 neighbors. So like think of like a 3x3 grid, and then you have to interpolate the value between all your neighbors around you. You might know this from Photoshop or somewhere where you have cloud filters, and it's just this like grayish, like pattern that is sort of like, it's dark gray, and then it like turns like lighter gray, and then it turns to white, and you have this like sort of like interweaving texture. But noise in our case, so we can use all of these. We can make use of all like these dimensions that we want. But for simplicity, I'm going to use only one-dimensional noise. And as we said, we only have this like, noise will return the same value for the same coordinate that we give it. So we need to like progress through the like maybe time, if you want to think of it like this. So we need to like progress through noise to like get a continuous like update on our values and like have it progress smoothly. We need to progress through the space. If this was like really weird, here's like a little code example. So I'm in the setup function in our sketch, which is called at the beginning and only once. We can have something that's just like keeping track of like the x offset of our little space. Let's start with 3, because why not? And then we update the state. So this is called before we draw something. In our update state, we just like assign a new, or like update x off. So update noise in this case would just like add 0.01 to the offset, and then we like put the new offset into like back into our state, which is then picked up by draw state, where we from the offset generate the noise, then map the noise to in this example to the width of our canvas, and then we draw a circle. And this is just to like noise for me at the beginning was very like, I don't think I get it, and I hope this is kind of like explains it as the dot now moves according to noise. So this like every time, like on every frame, and this is now running at 60 frames per second again. 0.01 is added to the offset of x. So we like, as the sketch runs, we're like progressing through the harmonic line of values that noise gives us, and with this line, the little dot walks with us. Why a value? Maybe like why increasing this with 0.01? Because as you have like an harmonic line, if you make big jumps in the timeline of this thing, you would also see it would not just like look smooth anymore. You would have like, it's again jumping from like this side to this side, and it's just like what happened in between. It's like all the steps that you left out. So like if we increase this like in tiny steps, we have this like smooth movement. Okay, so this is like one thing that's just like moving along the x-axis. I think it would be even cooler if we like used it in like the x and the y coordinates. This is not two-dimensional noise. I'm just applying one-dimensional noise, but in like both x's. So I have the same thing here with like the mouse. So I'm like opening the an extra tab. So we can do this. So I'm basically doing the same thing. I'm like, wherever I click, I create, like I memorize the point where I click, and then I define a little like frame in which I can have, which I can like map range our little like noise to. And yeah, and then the little dots like start bubbling. And this is like, aren't they smooth? I think this is nice. Fun. And it looks good through the constraints of the normal distribution, and also like the kind of like we chose the colors. It's like it cannot look bad, but it's just like, oh, I could do this forever. Look at them. Oh, great. I love it. Cool. Still, the only interaction that we did so far was we like clicked and then new things appeared. This is boring. But I kind of like, if I want to give a piece of software to someone, I kind of like also want to restrict them. I don't want them to have a bad experience. I kind of like only want to give them a little bit of interaction, but not too much, because we know users can like potentially ruin everything for us. Let's talk about vectors, but not the data structure. Let's talk about Euclidean vectors. So this is like from a different, like it's math basically. Vectors, you might remember that from school. Vectors hold a direction and a magnitude. And we can define vectors with by like keeping state of like an x and a y value on a coordinate system, and then like say it's like, okay, if you have this point here and then we like point to this other x and y coordinate, we can from there on calculate the direction and the magnitude. Why am I telling you this? With like simple vectors, we can already like start simulating forces and like little physics systems that we want. It doesn't have to be like real physics. We can like make up our own physics because we're gods in our own programs. So very, very simple. Physics could be like, we have a force that acts on a body, and it's like the force influences the acceleration of the body, which influences the velocity of the body, and the velocity of the body will influence the location of the body. Cool. This could look like this. I created a create dot function. It's already like keeping sort of like a lot of things for us. So we give it, when we create a dot, we need at least an x and a y. This is where the dot will be located. And then I have just like a map. And then we have, under the log key, I keep track of like the location vector. I have a velocity, like vel key, that keeps track of our velocity vector, the same for the acceleration. You can also see like how I defined the x and y offset values for the noise that we're gonna use. And in this case, I'm just saying like, pick a random start value for your noise offset, somewhere between like 0 and 100,000. And this is important. So if I gave the same starting point to each circle when I spawn them, they would all be like, they will all move in the same kind of way, and it looks really creepy. It's just like all of them move in the same way. It's just like, this is not cool. This is weird. I don't want this. And the rest is basically the same, like normal and custom distributions for radius and the hue, saturation, brightness. Okay, in the update state function, we will now like apply force to our bodies, And the add vector function is basically just take the x from both vectors and combine them, and take the y from both vectors and combine them, and then return us a new vector with the new x and y. And I do this so acceleration will be whatever acceleration was before plus force. Velocity will be what velocity was before plus acceleration, and so on and so forth. Then we like wrap this and like, because if we start applying force and you don't pay attention, like all your dots will like flow off the canvas, and you're just like, I don't get them back. So I'm kind of like wrote a little like wrap edges. So if the dots leave on one side, they spawn on the other again. So we like always keep track of them. And then I still have this like little noise thing that we see in the next example. One thing, I actually only persist the new location vector on the dots in my overall state. This might seem counterintuitive since I like define as this like location and the velocity and the speed, but this is like in this case it doesn't make sense. But you can also like play with what happens if you only keep track of velocity and not the acceleration, like make have other things like be forgotten as you update and like add, and this like all these like weird things that might happen of like surprise outcomes. But this is up to you. Once we then draw the circles, I just generate the noise, and then I also so we have force interacting with the dots, but then we also have like still the noise that is like making like the dots like look smooth and cool. Okay, last demo. So I have a couple of dots, and if I now click and drag, I apply force to them, and then they like wobble around. And you see it's like the closer I get to the center, like weaker the forces that I apply, and like the further away from the center, I drag the mouse. Like the stronger it is, like the faster the circles wobble. And this is kind of nice, but it would be even cooler. So I have a fig wheel running. So if I go to like the vector sketch, and instead of like spawning 10, I spawn 150. And yeah, I need to reload this. And I have a lot of circles. And then I have like little like, I don't know, beautiful things. Tiny little beautiful things that wobble around. And you can play with this, and it's really nice, and I really like it. And I'm like already running over time. My point is mix and match. These are like very, very, very simple building blocks for you. And if you use Quill or like any sort of processing, random Gaussian, and noise are like available to you, and you just need to like play with the things. I hope you got an overview over how to use them. So yeah, we learned about normal distributions, custom distributions, and noise, vectors, and like simulating forces. I'm gonna be thrown off stage. No, use them on colors, shapes, and sizes, locations. Use them on time. All of these things. Get people input. Like you can have them manipulate values directly. Have them manipulate inputs to the algorithms, or just like make them think that they can manipulate stuff, but then they can't, and like see how long it takes for them to figure out that they can't actually do anything. And this is, we can all be artists with like little bits of code. Resources that I recommend, and this is it.